So, okay, so I recently joined the Taipei Medical University and Shanghai Hospital last October. Yeah. So during this whole research, I was already interested in the consciousness. So I can briefly introduce myself as a cognitive neuroscientist investigating neural mechanisms of consciousness. Okay, so today I have like some aims. So as I mentioned, I want to introduce my research on brain-heart interaction at the beginning, and then another line of research on brain-lung interaction. And then I want to more focus on discussion for the future collaboration. Okay, so this is the main research question: whether or how the brain-visceral interaction affects our conscious perception and action. So, as I mentioned, I'm mostly interested in brain-heart interaction and brain-lung interaction. So today I will introduce three research. So first study investigated how interaction between the heart and brain can influence our visual perception, like how we perceive the flower in our environment, how brain-heart interaction affects such visual consciousness. And second research, I investigated how our self-consciousness, here I mean how we perceive ourselves. So like when we see our hand, when we have feeling, sensation that it's my body. And again, I will show my previous research, how the brain-heart interaction underlies such the self-consciousness. And lastly, the most recent research, I investigated how the interaction between brain and our breathing system affects our voluntary action. So voluntary action means our ability to initiate our action whenever we want. So I will investigate how the breathing system affects our voluntary action. So, but I think today the main aim is to introduce my research and discuss about the collaboration. So I think I will not go too much in details. I will focus on explain the general idea and the general message and for the future collaboration. Okay, so before introducing this study, I want to give some general background. Okay, so this is very philosophical background. So like Aristotle, who was the philosopher and also biologist at the time, suggested our heart is the seat and source of sensation. Of course, we know it's not correct. It's brain, not the heart. But this still convey the message that people have some intuition that our heart has some potential role in our sensation. And more recently, like the famous psychologist William James proposed our emotion is the feeling of bodily changes. So he famously claimed when we see a bear, we feel fear because of our heart beat faster. So, and another neuroscientist, Antonio Damasio, he linked this brain-body interaction to our self-consciousness. So inspired by this kind of the previous theories, during my PhD, I proposed this brain-body interaction can underlie this kind of diverse conscious experience. So in very brief, we propose this brain-body interaction is the neural mechanism of our subjectiveness. I will not go too much in this. This is very conceptual discussion. If you're interested in, you can check the paper. And at the same time, this idea has some neuroscientific background. So maybe this is more appealing to you. So our brain is not static. So our brain always fluctuates all the time, even we don't do anything. So like in our brain, there is a resting state network, which fluctuates all the time when we do nothing. So there are two research lines. So one research suggested that the potential role of our resting state network is the controlling our bodily state, like a heart rate, respiration, skin conductance. That's why the resting state network is so busy, even when people do nothing. That's one research line of research. And another research suggested this fluctuation of resting state network can affect our sensory motor processing. So how we perceive, how we act, this fluctuation of resting state network can affect. So, but at the time, no. So our idea is simply linking these two research lines. So how this bodily signal can affect our sensory motor processing, potentially through the fluctuation of our resting state network. So we wanted to link the sensory motor processing to the bodily signal through the brain. So that was the main idea of the main background idea over the other study I will present. Okay, and then next question is how we investigate the brain-heart interaction, for instance. Indeed, I think when I started my PhD, like almost 8-9 years ago, I think there are some like proposals, theoretical proposal, brain-heart interaction is important. But at that time, people kind of didn't have the method how to investigate the brain-heart interaction, for instance. So actually, it was my previous supervisor. She suggested me to investigate this measure called the heartbeat evoked potential. So it was introduced like almost 30 years ago, but I think people kind of forget about that measurement, and it was really not popular at all at the time. So this heartbeat evoked potential is simply measuring your neural response to heartbeat. So it's exactly the same like the visual evoked potential. So to investigate your neural response to visual stimuli, you simply time lock your electrophysiology signal, time locked to the onset of the visual stimuli. So this is exactly the same logic. So to investigate your neural response to heartbeat, you measure any kind of electrophysiology signal together with your ECG signal. And then you simply time lock your brain signal, time locked to the ECG, RPIC. So this is kind of based on the assumption that in animal studies showing that at each heartbeat, the heart sends the electric neural signal to the brain. So there are mainly two pathways like spinal cord and vagus nerve, and through the brainstem, the signal from heart is relayed up to the cortex. Like the insula is the main viscerosensory cortex, and anterior cingulate cortex, and even the sensory cortex because of this tactile sensation. So actually, when I started this research, there was we couldn't find very convincing evidence at the time. So one of the first work we did was providing a strong experimental evidence we can measure this neural response to heartbeat in human brain. So for that, we analyzed this intracranial EEG signal. So at the hospital, there was some hospital, and so we worked together with some epilepsy unit. So when there's patients, and when the patient has the electrodes in the insular cortex, which is known viscerosensory cortex, we recorded this intracranial EEG signal together with the ECG. And as I explained, we simply time locked this intracranial EEG signal to the ECG RPIC. So as you can see here, around after 300 milliseconds, you can see this phasic and transient neural response in the insular cortex compared to baseline. So this is kind of the strongest evidence that this neural response to heartbeat can be measured in human brain. Okay, then now I will introduce the first study. So in this study, we used the visual detection paradigm. So it's very classical and simple experiment. So in brief, there is this visual stimuli at the threshold level, which means just very weak. So if you see this visual stimuli hundreds of times, because it's very weak, you can detect it around 50%. Even the stimulus is constant all the time. So it's very weak stimuli. So during the experiment, the participants conducted this visual detection experiment, and we measured this MEG and ECG signal together. And actually the experiment is really simple. So, and then we analyzed this neural response to heartbeat just before the stimulus was presented. So imagine, because of your heartbeat, your heart is always beating, there is always your neural response to heartbeat all the time. And we analyzed this neural response to heartbeat just before you detect or couldn't detect some visual stimuli. And we analyzed how this neural response to heartbeat can predict whether you have visual consciousness of this weak visual stimuli or not. So this is the main results. So we found actually the differential neural response to heartbeat when they detect the stimuli or couldn't detect the stimuli, so hit and misses in the right frontal region. So here time 0 indicates the ECG R peak. So around ECG T peak, sorry. So it's around 350 milliseconds after ECG R peak. Your brain response to heartbeat was different. And when we analyze some correlation analysis, actually this amplitude of the neural response to heartbeat is positively correlated with their visual detection performance. And when we analyzed the neural sources, we found this cingulate, ventral medial prefrontal cortex, and right inferior parietal lobe. So this region is kind of known the main node of the resting state network. So it kind of supports our idea, your brain-body interaction in the resting state network can affect our perception and action. So I think there are two main messages in this study, general message, as I mentioned. Until we published this paper, people really didn't care about this measure, neural response to heartbeat, and there are not well-established methods how you investigate the brain-heart interaction, although there are some theories like the Antonio Damasio and so on. So this study kind of showed using this neural response to heartbeat, you can investigate the brain-heart interaction. Indeed, after this study was published, I think many people analyzed this neural response to heartbeat. Like at least there are 100 papers analyzing using this method. So title, I mean, you can imagine like the like brain-heart interaction in memory or attention, and people analyze this method. So I think that's the one general message. And second message is that, as I mentioned, even the ancient philosophers like Aristotle said something potential link between our heart and brain. This was kind of the first experimental evidence, indeed showing that your heart is playing some role in our visual perception. Okay, and second study, so this was, the first one was conducted in France during my PhD, and then I moved to Switzerland. So this was the first study during my postdoc. So then I changed the topic a little bit. So I started to investigate the self-consciousness. So self-consciousness, I mean, here we mean the self-identification. So how we identify ourselves. So investigating self-consciousness is very difficult because almost by definition, our self is kind of constant. It doesn't change a lot. So it's very difficult to experimentally investigate because it's constant. So in my previous laboratory in Switzerland, so my previous lab developed this nice experimental paradigm using virtual reality and head-mounted display. So to experimentally investigate our self-consciousness. So as you can see, the participants wear this head-mounted display. So, and they see their virtual avatar in front of them. And at the same time, the experimenter give this tactile stroking on their back. So imagine you are watching yourself in front of you, and you feel the touch on your back, and you also watch your avatar is being touched by this stick. So when your touch on the back and the stroking on the avatar is synchronized, you have stronger self-identification with the avatar compared to the condition when these two are asynchronous. So when you're touchy and this stroking on the avatar is asynchronous, like the 500 millisecond delay, people have some weird sensation. Oh, that's less likely in my body. So this is simply the results showing the strength of the self-identification during synchronous condition and asynchronous condition. So this is very nice way to investigate your self-identification. So in this study, we simply combined this behavioral paradigm and the analysis of this neural response to heartbeat. This is like the I don't know, maybe you familiar with this Antonio Damasio. He's really famous in this self and brain-body interaction. He proposed this idea of brain-body interaction is important for self-consciousness for 20, 30 years. But there is no strong experimental evidence at that time. And this was kind of attempt to experimentally prove this kind of the hypothesis. So it's again very simple. So while the participants were being stroked synchronously or asynchronously, we simply measured EEG and ECG signal and analyzed this neural response to heartbeat separately between these two conditions. And again, we could find the stronger self-identification when this stroking is synchronous. And then we analyzed this neural response to heartbeat while participants was synchronously and asynchronously stroked. And we found this differential neural response to heartbeat in this frontal central region. So in this experiment, it's very important to show there is no difference in ECG signal itself. So when we measure ECG, it's just the same between two conditions. And we only observe this differential neural response to heartbeat. So it is really transient. There is no difference before stroking start, but as soon as you stroke start, this neural response to heartbeat become different, and it becomes same again as soon as you stop the stroking. And then the questionnaire score measuring the strength of self-identification was correlated with this neural response to heartbeat. And the neural sources were in the cingulate region. Mm. So again, this is kind of the similar logic using already this neural response therapy. We show that this brain-heart interaction is kind of can influence our sense of self-consciousness. Okay, just and this is the then in this study I investigated how the interaction between brain and our breathing system can affect our voluntary action. So voluntary action, as I mentioned, is our also one critical aspect of our self-consciousness. So it's very simple. We can move our action whenever simply we want voluntarily. Okay, so I will give you very quick introduce in this topic. So it's the one of the most classical topic in this neuroscience, cognitive neuroscience. So already in 1965, this Konuber and colleagues showed that when we start our voluntary action, already almost 2 seconds before, your brain somehow starts to change, drift. 2 seconds before you start your voluntary action. So it's already kind of positive. How brain knows you will start action 2 seconds after. And then, like the 1983, maybe you heard about the Benjamin Libet, the famous Libet, experimentally measured when you have sensation that I want to move now. So using this Libet paradigm clock. So there's this rotating clock. The participants simply click the button whenever they want. And after they press the button, they simply report that at like here I had the sensation of intention that I want to press the button. But then the results suggest that it's only 500 milliseconds before they have sensation that I want to move. So imagine these results together suggest when you start your voluntary action, 2 seconds before your brain already somehow drift, and then 500 milliseconds before you have sensation, okay, I want to move now, and then you press button. So really so basically there is like 1 second delay your brain activity, which is called the readiness potential, and your sensation of your movement, voluntary movement. So people are really puzzled. So some philosophers said, we don't have conscious free will because everything is already decided by the brain, even we have sensation of the voluntary action. So it was until like during last 50 years, it was really controversial. Why there is this gap between them? And actually, the most recent and prominent view on this interpretation is that people say this Schroeder and colleague propose this is just simply neural noise. Like the stock market price fluctuates, it's just a neural noise. And somehow you align this neural noise to this ramping up period. They just artificially show this kind of the drift. I still don't understand their explanation. I mean, if it's the simply noise, why it's the time locked to the peak? They don't explain it. They just say it's noise. But anyway, it's the kind of the very famous theory. Then again, so I thought maybe because of so in this study they proved this is just resting state fluctuation or noise. So this idea kind of fits. So previous study shows that maybe, so what we proposed is that maybe it's not the noise, it's the something linked to your bodily signal, in particular breathing system and the voluntary action. We wanted how this brain affects our motor processing, potentially through resting state network. So that was the logic behind. And also there are another reason we studied this is that like already from like the 60s, 70s, there are science papers showing your breathing is synchronized to your limb movement while running. And more recently, animal studies show that your breathing is affects the whisking in the mouth. So suggesting our breathing is one of the motor system, of course, and it somehow affects our like the another motor system. But most of these previous studies show that the breathing affects very low level motor function, like whisking or limb movement, basically for more efficient volitional processing. But what so this is kind of different because voluntary action is one of the very high level motor cognition. Like we don't need efficient metabolism. We just decide when we start our voluntary action. Okay, then okay, so as I explained, we used this classical Libet paradigm. And then we measure the EEG and breathing signal together. So this is the main results. So this is the kind of the histogram showing when participants started their voluntary action. So here, phase 0 indicates the start of expiration, breathing out, and here, pi indicates the start of inspiration, breathing in. So as you can see, if there is no relationship between the breathing cycle and the timing of voluntary action, it should be uniform. The distribution should be uniform. But as you can see here, it's people much more likely to initiate their voluntary action while breathing out. In particular, in this late phase of breathing. So imagine you're breathing out, and then they start their voluntary action. Simply click the button, and when they breathe in, people less likely start their voluntary action. And then when they finished, we asked them whether people aware of this relationship between breathing and voluntary action. And among 50%, only 1% reported they aware of that relationship. So most of people just don't aware, but still prefer to start the voluntary action while breathing out. So it's kind of this is one of the main finding. And second finding, and as I explained, we analyzed this readiness potential. So again, like 2 seconds before the readiness potential started. And then what we analyzed was this relationship between this readiness potential amplitude and the breathing cycle. So again, so this axis indicates the respiration phase from expiration. So there are 6 phase beans. So here expiration, here inspiration. So in other words, so this results show that this readiness potential amplitude is synchronized with the breathing cycle. So taken together, this results show that there are close interrelationship between your breathing cycle and timing of your voluntary action and your breathing, your brain signal. Yep. So as I mentioned, people are really puzzled why the brain readiness potential starts before your conscious intention. So our results suggest, so this is at least partly reflect your breathing related brain signal. It's not the neural noise. Also, it's not like they know you will move. It simply reflects your brain signal controlling your breathing. And then, so yeah, yeah. So this kind of provides the physiological explanation of this kind of mystery. Mm. Okay, so and then this is the kind of follow-up study. So I mean, when we found this result, we were kind of surprised how the breathing system can affect our voluntary action. But once you understand, it kind of makes sense because breathing is also this we can voluntarily control, and it's also encompass this motor component. Although usually spontaneous breathing is involuntary, it is still motor, and our hand motor is also motor. So it kind of makes sense, interaction between very high level motor function and very low level hand movement. And then we were kind of curious. Then this influence of breathing is limited to our hand motor function or not. In other words, like our voluntary mental decision will still influenced by breathing cycle. That was our next question. So indeed, so we did another experiment just before I moved to Switzerland. So the experimental paradigm was exactly the same, except now the participants don't press the button. They just there are two conditions. So in one condition, they just imagine they are pressing the button. So which is called motor imaginary. In another condition, they imagine something just visual. So this is called visual imaginary. So because on the screen, the clock hand is rotating. So we instructed participants to just imagine taking a mental screenshot to stopping the rotation clock hand. So there are two conditions, motor imagery and visual imagery. And then we analyzed how this onset of motor imagery and visual imagery is linked to your breathing cycle. So because by definition you don't do anything in this imagery condition, so the timing of the task was relied on the report at the end of each trial. So they verbally reported when they did the task. So again, we can find this voluntary mental action is still linked to your breathing cycle in a similar phase. Even they don't need to move their limb, still the decision of the voluntary mental action is anchored or coupled to your breathing cycle. So this just to show the statistical results, and this just to show the EMG measurement, measuring the finger movement. So there is no finger movement at all, but still the timing of the mental action is linked to your breathing. So I think it's a bit crazy. I mean, yeah, why? So in terms of neural mechanism, it kind of makes sense because there is this supplementary motor area. It's known that the supplementary motor area control our voluntary action, whether it's motor or even our mental planning. This supplementary motor area underlies such the preparation or planning of our action. And recent studies show that this The supplementary mole area also reflect the control of your breathing pattern at rest. So we kind of propose that this interaction occurs at this the supplementary motor area. Okay, so this is suggest kind of the influence of breathing is really broad and general. Even it's not motor action, it still affects the timing of our mental action. I think it's very interesting. Yeah. Okay, so these are all the results, and we still plan a few follow-up studies. Just 1 second. Yeah. Okay, so I have still time. Sorry. Mm. Okay, so I have ideas on a few follow-up studies. So first, so we showed that the breathing affects our timing of our mental action, motor or mental action. But still there is some alternative explanation. Maybe it's not it's just due to the oxygen level in your brain, right? So when you breathe in, the oxygen level increase, and it's simply due to the change in oxygen level. You somehow press the button more frequently or not. So to test such an idea, um, we are thinking about this follow-up experiment. So this ventilator kind of control the breathing pattern. So when the switch is when the this machine is on active mode, the subject doesn't need to actively breathe. So they just open their mouth and the air goes in and out. So they just they doesn't need to actively breathe. So it's kind of induce this passive breathing mode. And usually we actively breathe, right? So using this machine, we can make this two active or passive breathing mode in participants. So our prediction is that during the passive mode, so the air goes in and out, but they don't actively breathe. Such a coupling will not be observed. So in other words, our prediction is that this kind of active action of breathing, that's what influence our voluntary action. Mm. Okay, and then the second idea is maybe we can measure this breathing and action coupling in meditators. So meditators, they are professional in controlling their breathing. So our hypothesis is that because of they are they are used to controlling their breathing, they will be less anchored, less constrained by their breathing. Meaning, we expect there will be weaker breathing action coupling. And then another idea might be because in normal health participants, we can observe such a breathing action coupling. Maybe some clinical patients like the Tourette syndrome or like the people have difficulty in voluntary action control, they have maybe abnormal breathing action coupling. So we can use this measurement as a kind of the diagnostic purpose. And actually, like 1 or 2 months ago, I visited the Professor Kang-Yun Lee's team, and we discussed another idea. The Professor Lee, we discussed about this dyspnea patients. So they have the difficulty in controlling their breathing, but still the usual cardiorespiratory parameters are normal. So this is kind of the idea also I discussed with my previous supervisor and another colleague in Switzerland and UK. So in our previous lab, we have this device using head-mounted display. So it's again using the head-mounted display, you see your virtual avatar in front of you, and at the same time, we measure your breathing pattern using this respiration belt. So imagine you see your body, and there is this visual silhouette flashing in synchronous or asynchronously regarding your breathing pattern. So this was used for another purpose. So what they found was that when this visual growing is synchronous to your heart beating, they have the stronger self-identification to the virtual avatar. So we have this setup. So imagine the patients wear this head-mounted display, and then they can see this visual flash regarding your actual breathing cycle, or something another. Sorry. Maybe I need to explain this first. So so maybe you heard about this model. So many people think our brain is kind of active inferencing machine. So they always predict about the consequence of our movement or sensory processing, and then we compare this prediction to the actual sensory signal, and we try to reduce the discrepancy between this prediction and actual sensory feedback. It's very popular paradigm, and people basically trying to apply this model to everything, like visual perception and action, or even how they breathe. So one potential issue in this dyspnea patients, maybe they have somehow difficulty in this process, prediction on their breathing and censoring, comparing this prediction to their actual breathing sensory pattern. So when they have some difficulty in this comparing process, they have difficulty on their breathing. So based on this idea and this technique, we kind of discussed, maybe you can use this as a kind of the therapy for these patients. So they, rather than synchronizing their own heartbeat, they simply see this change in visual flash synchronized to some normal, healthy people. So it provides some normal prediction of their usual breathing pattern. And by training to get used to this kind of the normal breathing pattern, maybe this can be improved. This comparison processing can be improved. So yeah. So we are discussing this project with Professor Lee. Yeah. Okay, and indeed, I'm very much interested in applying this kind of the brain-body interaction research to mental disorders. So at the moment, we have this working hypothesis. So it's very general. So abnormal state of brain-visceral interaction might be related with the mental disorders, in particularly associated with consciousness and emotion. Indeed, I did another clinical study, so I can introduce briefly. So this study was in nightmare patients. So people who have difficulty in emotional regulation while sleeping. So actually, this was the collaboration with the another laboratory. So while we just discussed about the potential collaboration, they suggested that they have some EEG data in nightmare patients, and they also had the ECG recording. So we just agreed analyzing this neural response to heartbeat in this nightmare patients. So this is the neural response to heartbeat while sleeping in nightmare patients and healthy controls during REM sleep, REM sleep. So, and this is the differential neural response to heartbeat. So as you can see this differential neural response to heartbeat during REM sleep between nightmare and controls. So this kind of difference was observed only during REM sleep, but not the other sleep stages. And interestingly, this kind of the differential level was correlated with their mood score in nightmare patients, suggesting this neural response to heartbeat is correlated with their inability to regulate their emotion in nightmare patients. So it is rather really, I don't know, it's kind of good example of collaboration. I think I spent 1 or 2 months for analyzing the data because they already had the data. I think they spent almost 1 year to record the data, but because they already had data, the study can be finished really quickly. Yeah. And I also another collaboration regarding schizophrenia, because some research proposed that schizophrenia is they have some deficit in their self-consciousness, recognizing their own and others. So again, so they had the nice MEG data for 45 patients and 45 healthy controls, and they kindly agreed to provide the data. So actually at the moment, I'm analyzing this data, the neural response to heartbeat in schizophrenia and controls. And lastly, there is another, because I was in Switzerland, Geneva, there was Geneva University Hospital. We had some collaboration with the neurosurgeon unit. So we had some national grant from Switzerland. So the neurosurgeon, they very often have some surgery due to the tumor. So they often resect like a tumor in insula or some like the other brain areas. And then we see how the resection in this insula or other visceral sensory region affects their self-consciousness or yeah. Okay, so I hope I can develop this kind of the clinical collaboration with KMU and Shanghai Hospital researchers. Yeah, and this is the last slide. So I recently got the accepted grant support by the MOST. So 2 grant proposal, and I really appreciate for that. Yeah. Okay, so thank you very much for your attention.